All right, these are video notes on simplifying radicals, a lesson that we did on Monday, October the 26th. First thing you need to remember is that the radical symbol is typically what we know of as the square root symbol. It's called a radical because you can still draw the same symbol, and yet it can represent other roots. Okay, it's typically called a square root because we're taking the second root. Now, when I say that that same symbol, the radical symbol, can be used for other roots, we could also take the third root of a number. We could take the fourth root of a number. We could take the fifth root of a number. Now, what I've done is I've placed a little number in the corner of the symbol on the left-hand side. Typically, we do not put a number, but if you don't put a number in that little corner there, that's called the index. It's understood to be a 2. So that's where it says you're taking the second root because you're understood to be taking the second root. What that means is I'm asking myself what times itself twice is going to give me what's underneath. If I take the third root, I'm asking what times itself 3 times is going to give me this. Like, what's the third root of 8? Okay? Or the third root of 27? Or the third root of 1,000? Okay, I'm asking what number times itself 3 times is going to give me 8. That answer would be 2. The third root of 27, what number times itself 3 times is 27? That would be 3. 3 times 3 times 3 is 27. What number times itself 3 times is 1,000? That's 10. 10 times 10 times 10. So if you can take the third root, you can also take the fourth root, the fifth root, and etc. I actually have the first 15 perfect squares on the board. 1 squared is 1. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. I have those on my board for quick and easy reference. I also have the first 10 perfect cubes on the board. So if I said 1 to the third, 1 cube, that's 1. 2 to the third power is 8, because 2 times 2 times 2, 3 times is 8. 3 to the third, we just looked at it, was 27. 4 to the third actually is 64, and the numbers get quite large after that. So for quick and easy reference, these are written on the whiteboard in my classroom. All right, strategies to help simplify. As we get ready to do the first examples on the next sheet, on the next slide, which will match up to what you have there, if you want to pause this video and write these notes, add these notes to what you have there. Number 1, I would say look for squares. Look for a, well, not really a 1. Look for 4 or 9 or 16 or 25 or 36. Look for those numbers that will divide into your number. And again, I have these on my board that we can quick and easy see when you work in the classroom. But look for squares first. That would actually be the easiest thing you can do. Number 2, you can factor the number out. Even if you don't get the squares, you can still think of 2 numbers that would multiply to give you the number that we're looking for. So factor the number out. And then number 3, the strategy that never fails you is for every 2 factors alike, pull one out. And the reason it's for every 2 is because I'm taking the second root. So if I ask you, what's the square root of 25? Then you would probably say, oh, that's a 5. What's the square root of 36? Well, that's a 6. What's the square root of 4? Oh, that's 2. And we know a lot of our square roots, and that's why I say look for squares first. But I want you to realize that that's really 5 times 5. So for every 2 5s, I'm actually bringing out 1 5. Okay, because you're asking what a number times itself twice, and that 5 is the number. 6 is really 6 times 6. For these 2 6s, I pulled out what? 1 6. This is really 2 times 2. So for every 2 2s, I pulled out what? 1 2. So whether you remember your squares and you do it that way, or you think about breaking it down to where you have 2 factors alike, pull one out. All right, so here's the first few examples, the first 3. And what I want us to do is we're going to observe that 20 is not a perfect square. If I look at my board, I see that 4 squared is 16, and I see that 5 squared turns out to be 25. So there isn't, 20 would fall in the middle. There is not a nice, neat whole number that's going to give me the square root of 20. And I'm not asking you to use your calculator. We're not going to use the square root key. So that square root key that you see on your calculator, we're not using it for this lesson. I do not want to see decimals. I want you to use other numbers. All right, so the first thing I want you to do is ask yourself, look for squares. What times itself will give you 20? Hopefully one of those is a square. Okay, I hope that you think of 4 times 5. All right, and if you think about 4 times 5, now you can actually look at just this part. What is the square root of just 4? Okay, square root of 4 turns out to be 2. So I'm going to pull a 2 outside of the radical symbol. Turns out, though, the 5 factor cannot be pulled out, and I cannot break it down any farther. So I'm going to end up with a 2 on the outside because square root of 4 came out as a 2, but the 5 stays underneath. 2 square roots of 5, or 2 times radical 5, is the simplified form of square root of 20. So this to this is what we're called simplifying radicals. So that's why we need no decimals. All right, let's do the second example. We're asking ourselves what times itself is going to give me 54. So 54 would be, I'm going to try to think of squares first. 4 is a square. 4 doesn't go into 54. 9 is a square. 9 does go into 54. 9 goes into 54 6 times. So now I'm going to ask myself, what's the square root of 9? Square root of 9 is a 3. So I'm going to pull a 3 outside the square root. Can't really pull out the 6 because there's no perfect square that's got 6. So I have a 3 on the outside of the square root and a 6 that remains under the square root. So 3 times the square root of 6 is the simplified form of square root of 54. All right. Example 3. Square root of 18 is not a perfect square, but I want to break it down into 2 numbers that would give me 18. So if I can think of a perfect square, I would do 9 times 2. 9 times 2, if I think about square root of 9, what's the square root of 9? 3. So I'm going to bring a 3 out. So a big 3 comes out, and underneath the square root remains a 2. I can't do anything else with 2. That's as small as it gets, and there's no square that goes into 2. Now, an alternate solution. Let me just show you an alternate solution. If you don't get your squares, like I had students that said 18 breaks down into 3 times 6. Exactly right. Neither one of these is a square, but I can still factor it out. That's strategy 2. Factor it on out. So I'm going to take 6 down even farther. I'm going to take that down to 3 times 2. Now collect every end of your branch, and now you've broken 18 down into 3 times 3 times 2. So 18 is really, the square root of 18 is really 3 times 3 times 2. Now, the third strategy, the one I said would never fail you, is for every 2 factors alike, do what? Pull 1 factor out. So I was able to pull out a 3, and for those 2 3s, now I've used those. And remember, 3 times 3 is really what? 9. So when I was doing this up here, I hadn't broke it down to 3 times 3, but I still pull out the 3 and leave the 2 inside. Okay? Notice that I got the same answer, but I just did it 2 different ways. Here I got my square first, times 2. Here we use 3 times 6, but if you kept going, you still got your 2 3s. You pulled a 3 out. You try. Okay, you can pause the video if you like. I'm going to go ahead and go with the solution, but if you want to pause it, go ahead now. All right, hopefully you tried these and you were able to ask yourself what times itself is 63, and that would be, 9 times 7. So 9 times 7, square root of 9 is what? 3. So 3 comes outside, 7 stays inside. Did you get that one? I hope you did. All right, what about 50? Square root of 50. I hope that you got 25 times 2 because 25 is a perfect square. What's the square root of 25? That's 5. So 5 comes out, 2 stays in. 5 on the outside, square root of 2 on the inside. I hope that you successfully got example 4 and 5. All right, what if a coefficient or a number is already out there? Okay, so even before I work with 75, I already have a 2 out front. Okay, that's simple. What you're going to do is you're just going to multiply by that factor when you bring yours out. Okay, so let's just work underneath first, and we'll do this 2 next. All right, asking myself what multiplies to give 75? Hopefully a square. And 25 is a perfect square. 25 is like a quarter. And there's 3 quarters and 75 cents, so 25 times 3. Now, there's still a 2 out front because that's what I had to begin with. What is the square root of 25? The square root of 25 is 5, so a 5 comes out. I already had a 2 out there, so what I'm going to need to do now is multiply by that outside factor. So the 5 that came outside is going to multiply by the 2 that was already there and give me 10. Now the one thing that could not come out is the 3. So that gave me the final answer of 10 square root of 3. 10 times the square root of 3. So again, when I brought the 5 out, I multiplied by the 2 that was already there. All right, same thing here. How would I break down 40? I hope that you get 4 times 10. Instead of do 8 times 5. 4 times 10. If you did 8 times 5, you could still do it, but you have to break 8 all the way down. Square root of 4 is 2. So now I brought it out as a 2. Now there's already a negative 8 out there. So what do I do with a negative 8 that's already out front? I'm going to multiply by that number already out front. So 2 times negative 8 is negative 16 out front. And then it looks like 10 stays underneath. And 10 cannot be broken down any farther. Okay, so if you have a coefficient already out there, whatever you're able to pull outside the radical symbol, make sure you multiply on the outside. All right, what if variables or monomials appear under the square root? All right, then simply you're going to do the same thing that we've said. For every 2 variables alike, pull one out. Pull one out. All right, so I'm going to work with 8. Okay, and I'm going to work out this time the whole full thing. I'm going to draw it out. That's going to actually give me 4 times 2, and 4 is a perfect square. So that's what I'm trying to do. Is I'm always trying to think of perfect squares. All right, that's going to really be x times x. If I take x squared and break it down, I get x times x. Okay. For every 2 factors alike, pull one out. All right. That's really 2 times 2. And square root of 4 is 2. So 2's come out. Yeah, so I know I'm going to end up with a 2 on the outside. There's one 2 that remains, and I will not have room to bring that 2 out. I can't bring it out. There's 2 x's. For every 2 x's that are alike, for every 2, pull one out. So I can bring one x outside, and I've taken care of those x's. And when I do the square root of 4, I've taken care of the 4. So x came on the outside, and only a 2 was left on the inside. So for every 2, pull one out. Every 2, pull one out. Okay, let's do this one. Okay, how can I break down 32? You could do 8 times 4. 4 is a perfect square, but then 8 can be broken down again. So there's a number bigger than 4 that's also a square that goes into 32. Turns out 16 goes into 32, and 16 is a perfect square. So I'm going to remember 16 because 16 is my perfect square, and 16 times 2. Now I'm going to show you y cubed is y times y times y. Z to the 4th is z times z times z times z. Now I don't want you to have to write all of this out every time, but we're going to write it out this time just so you can see how it works. And when we do the next example 3, we will not write them all out. Okay, so now I'm going to start thinking about what gets to come out. Well, square root of 16 I know comes out as a what? 4. 16's been done. 2 can't come out, so it has to stay. For every 2 factors alike, pull one out. So I have 2 y's. There's an extra y, but these 2 y's, for those 2 y's, I'm going to pull out a 1y. This y has to stay. For every 2 z's, I can pull one out. So I got 2 here. I'm going to pull out a z. Those 2 are gone. Okay. I have another pair of z's. So for these 2 z's here, I'm going to be able to pull out yet a second z. And notice there are no z's left. So I'm going to have on the outside a 4, a y, and 2 z's, which I can actually simplify as z to the 2nd power. What's left under the square root is a 2 that couldn't come out and a y, an extra y that couldn't come out. So I have 2y under the square root. So 4y to the 2nd times the square root of 2 to the 2y. All right, one thing I want you to imagine, I do not want you to have to write all of this long problem out every time with your letters. That takes a lot of room, and it works, but it's still very, very roomy. It takes up a lot of space. So what I'd like you to do is when you look at your x's, like here we have x to the 2nd, y to the 4th, z to the 6th in example 3. What I want you to do is I want you to ask yourself, how many pairs of x's do I have? Well, if I have x to the 2nd, I have what? I have 1 pair. 1 pair. If I have y to the 4th, right, that's y times y times y times y, I have what? 2 pair. Okay, so basically what I'm doing is I want you to imagine, what if you had 6 z's. How many pairs is that? Well, I hope that you know that that would be what? 3 pairs of z's. Okay? So imagine pairing them up, and only for every 2, pull 1 out. So I don't want to have to write it all this time. I am going to break down my number. Does anybody know how 98 breaks down perfect square? Turns out it's 49 times 2. Okay, 49 times 2. Now, what's the square root of 49? Square root of 49 is 7. So a 7 comes on the outside. 2 is going to have to stay, and I've used the 49. All right, now I want to jump back up here, and I want to ask yourself, how many pairs of x's do we have? Because every 2, I'm going to pull out how many? 1. And we just said there's only 1 pair with my x's. All right. How many y's do we have? How many pairs of y's? Well, we said that there were 2 pairs. Y to the second. So we're just going to try to bring them out and imagine thinking it through. Z to the 6th. How many z to the 6th? Well, there are 3 pairs, or that'd be z to the 3rd. It turns out the final answer for this problem is 7 on the outside, x on the outside, y to the 2nd, z to the 3rd on the outside, and the only thing that remained underneath was square root with a 2. All right? So when you look at your letters, I want you to imagine pairing them up. For every 2, pull 1 out. Basically, it's like you're dividing by 2. You also want to observe that if you have an odd number, look right here. When you were looking at y to the 3rd, you had an odd number of y's. So it's like having pairs, but then you've got an odd one. Like imagine shoes. If we went around the room and we picked up 3 shoes and we put them together, and you say, well, I've got my pair, but I've got this one odd shoe. I must have missed one somewhere. Maybe one's under the bed. So anyway, I've got an odd number. So if I have an odd number, notice that in my answer, I had that odd extra y was still under the square root. So odds are going to leave you with something under their square root. But if it's an even number of x's, like the first one had an even x, all of those came out and there was nothing left underneath. So that's the end of the lesson on simplifying radicals.